So the reaction is reversible, R giving P, P giving R. And the rate constants for the forward reaction is Kf, backward reaction is Kb. At time 0 we start with only R, and after some time at the end we have some concentration of R and P such that the rate constant Kb is 4 times that of Kf. So which means that the reaction will kind of look like backward is 4 times larger, so something like this, and 4 kf is the backward rate constant and Rp, which means let's just quickly have a look at the options. In the options A, B, C, D, we see that there is some quantity concentration of R by R naught, and there's another quantity concentration of P at any time divided by R naught. So comparing these, let's write the rate equation for forward reaction, which will be Kf times the reactant R, and the backward reaction rate will be Kb times reactant P. Kb is 4 Kf. After sufficient time has passed, what happens is equilibrium is reached, where the rate of forward reaction and backward reaction are same. So at equilibrium, Kfr, this is at any time t. It's a variable, so it takes this value. Let's say R equilibrium, R at equilibrium equals Kb 4 Kf P at equilibrium. So this shows us that R equilibrium is 4 times that of P, which makes sense. We started with R and no 0 at time t, and no P at time 0. So after some time, because the backward reaction has a rate constant which is larger, R is something that is in larger quantity compared to P at equilibrium. So this is one thing, and in order to arrive at the correct value, uh, we can conserve mass. So the concentration, it's a first order elementary reaction, which means order is equal to molecularity. This is why we could use concentration of R to the power 1 and concentration of P to the power 1 in the rate equation. So because at time 0 we start with only R, and the stoichiometry of the reaction says that 1 mole of R produces 1 mole of P. So we can say that concentration of R that we started with at time 0 plus concentration of P was 0 is the same as the concentration of R at equilibrium plus concentration of P at equilibrium. And from these equations we can find out equilibrium concentration of R and P, and that should be 4 P equilibrium plus P equilibrium equals R naught. 5 R naught. So P equilibrium is 1 by 5, 0.2 R naught. And similarly, R equilibrium will be 1 minus 0.2, so 0.8. This is the equilibrium concentration, and let's check the options. So A says that at equilibrium the concentrations are same, so A is wrong. Concentration of R at equilibrium is less than that of P, so B is also incorrect. C looks correct. Let's see D. It says that equilibrium is not reached and the concentration of P keeps on increasing, concentration of R keeps on decreasing, which does not happen. So D is wrong. C is correct. It is concentration of R by R naught starts from 1 and reaches 0.8. That of P starts from P by R naught starts from 0, reaches 0.2. So option C.